Today we're talking about the periodic table and a little bit of the underlying structure of the periodic table that makes it super useful to use in chemistry. Before we do that, I want to take a minute to review what we talked about last week in terms of atomic structure, because they start to it goes together really beautifully with the periodic table. So to review, there's three subatomic particles, as you all know, are protons, neutrons, and electrons. We know that protons and neutrons are the two that hang out in the nucleus, and that the atom is mostly space. It's surrounded by these tiny negatively charged electrons that are whizzing around in the space outside of the nucleus. The number of protons is determined by the atomic number. So if you look at hydrogen, it has 1 proton, vanadium has 23 protons, aluminum has 13 protons, and so on. In a neutral atom, it will also have the same number of electrons. A proton has a positive charge, an electron has a negative charge. Therefore, if we have that neutral atom, even numbers of the two will cancel each other out and make for a neutral atom. Number 4, isotopes of a particular type of atom have a different mass because they have a different number of neutrons in the nucleus. So each element on the periodic table has at least one isotope. Many of them have many. The mass number is something that is given to you, and you use that to figure out how many neutrons that atom has. Ions are created when we change the normal number of electrons for an element. This is the last one I wanted to briefly touch on because that's where we're kind of heading next, is that we can change the number of neutrons in an atom, we can change the number of electrons in an atom, and that will change how that element is behaving, but it still stays the same type. So we can make a gold ion or a gold isotope, and that's important as we go along. So some information here. The periodic table does have a variety of schemas that create its shape, and I've got to say the more you learn about it, the more fascinating levels there are and ways in which this tool can be used. One of the important things is, if you've ever wondered why the periodic table is called the periodic table, well, partly that's because these horizontal rows are called periods. It is also because of the periodic law, which states that if you organize elements by increasing atomic number, or back in the day, increasing atomic mass, you will have this repeating pattern of physical and chemical properties. So, but anyway, the horizontal rows are called periods, and these rows indicate how many energy levels have electrons in them in the Bohr model. So you'll remember that first Bohr model just can fit 2 in the first energy level, and so on from there. And those energy levels are split into orbitals and suborbitals. Number 3, the vertical columns on the periodic table are called groups or families. So these numbers on top, 1, 2, 3, and so on, all the way up to 18, those refer to group numbers or family numbers. And these columns are really helpful and really useful because they give us a lot of information about what the elements in this column's physical and chemical properties are going to be. And that's very useful and very important. So the vertical columns are called groups or families. They give us reliably predictable information about the physical and chemical properties of other elements in the same column. So remember, when the periodic table was made, sometimes there was an ability for elements to be predicted, like gallium, where they said, okay, we know there should be another element there, we just haven't found it yet, and then they would find it. So the last important thing I want to point out about the periodic table at this, the highest level, 30,000 foot level view of the structure of the periodic table is really important, and it's called the stair step. So on this one, it's a little bit faint. It's not as strongly drawn in as it is on the one from last semester. That's kind of the one drawback to this periodic table. You can see it very clearly here on this sketch of the periodic table. It is on all periodic tables. It's generally the stair step. And the deal is, everything to the left of the stair step is a metal, and everything to the right of the stair step is a non-metal. At the highest level that we can kind of break it into two, metals and non-metals behave very differently, and we're going to end up talking more about that, but it's just something I want to point out now. If you forget which side are the metals and the nonmetals, you can always find this line right here is copper, silver, and gold, or, iron, or chromium and titanium. Those sound more like metals, right? And it can kind of help you remember that this left side is the metals, because things like calcium and magnesium, they don't maybe sound as much in our personal experience as like metals, but they still behave like metals elementally. So 30,000 foot view, things towards the left side are metals, things towards the right side are nonmetals. So let's dig into these metal and nonmetal groups a little bit here. So group 1 is called the alkali metals, and that's this column right here. Hydrogen is not really in the alkali metals. It behaves more commonly as a nonmetal, but it does kind of like to break the rules, so it's over on that column as well. The column includes lithium, sodium, potassium, rubidium, cesium, and francium, and this whole group, the whole group is extremely reactive, and they are almost never found on their own in nature. They're always found in nature combined with other elements. The name comes from the fact that when you react any of this group with water, they create alkalis. Alkalis are very, very strong bases. So you get this really intense reaction with water, like we saw when we saw sodium roll down the hill into the lake in the video we had with sodium for the element of the day. But they also create these very strong bases, as evidenced by the cars in that story that had their car paint get messed up by the sodium hydroxide that was made by that reaction. One last thing about the alkali metals, they all have a silver-like luster, so they're pretty shiny. They're highly ductile, so you can pull them into wires fairly well. And not surprising as metals, they have high conductivity of electricity and heat. Moving on to group number 2, which starts here with beryllium, goes to magnesium, calcium, strontium, barium, and radium. Prior to the 1800s, I think in some ways this group is one of my favorites just because of the name background here. This group is 2, group 2, and it's named the alkaline earth metals. Well, where did that earth come from? And it turns out that, prior to the 1800s, these substances that were non-metallic and unchanged by fire and insoluble in water was known as earths. And that kind of, we had like this group here on the left, these metals that would explode right in water. And then we had like the aluminides or aluminides or something like that. I can't quite remember what the term was, with the metals sorted to the right. And these were categorized as more of a nonmetal. But what happened was in the mid-1800s, it became clear that these were oxides, that they were combined to oxygen and that they could be isolated down still further to be individual. And when that happened, it was much more clear that they behaved like metals. So it became clear that they were actually oxides. When they were able to separate them out, the group became the alkaline earth metals, kind of harkening back to that original name, and have been in group 2 since that original proposal of the table in 1869. These metals, like all metals, lose their valence electrons to nonmetals easily and form positively charged ions. If you think about electricity flowing in metals, it flows because metals do not hold on to their electrons tightly, and that is what allows electricity to flow through the metal and wires. So we'll see this kind of repeating pattern of how metals don't hold on very tight to their electrons. Group 3 to group 12, so this bridge coming across the periodic table is the transition metals. This group describes many chemical elements that have valence electrons, those outermost electrons, in 2 different shells instead of just 1. That makes them behave less predictably. We don't use them quite as much in general chemistry because of that. But all of the elements in that area are metals. Many are hard, strong, lustrous, have high melting and boiling points, and are good conductors of heat and electricity because they're metals. It includes a lot of the important elements to technology. So titanium, iron, nickel, and copper are all very important. And it also has this row, as I pointed out earlier, that's the precious metal kind of row The lanthanides and actinides, so these two series right here, they both fit into this zone right here. So their reactivity basically puts them right in this spot. And because they also all have unfilled f orbitals, it's like they can't all fit into that one zone. And so they get kind of put out as the little landing strip here. But they are part of the transition metal groups there. Moving on, going to go ahead and skip over the other metals and the metalloids. Those are important, and they are becoming a little bit more important in our world in terms of technological uses and batteries types of stuff in particular. However, we're going to kind of skip them for now. Group 15 to 17, right in this zone. These are all nonmetals, all right? And specifically carbon, nitrogen, oxygen, phosphorus, sulfur, selenium, and hydrogen are nonmetals. Those make up all living organisms on our planet are made up of nonmetals, and primarily carbon, nitrogen, oxygen, and hydrogen. None of them conduct electricity because they do not give away electrons easily. They would rather steal them. Group 17, so this group right here is still technically broadly categorized as a non-metal group because it's on the right side of that stair step. This group includes fluorine, chlorine, bromine, iodine, astatine, and tennessine. It's one of the new ones there. The name comes from the Greek roots hal and gen, and together that meant to produce salt. Salts chemically are when we take one of these non-metals and combine it with one of especially these first two column metals. But anytime you take a metal and a non-metal and put them together, we call it a salt. Not all salts are edible, but table salt, NaCl, is an example of one chemical salt, and that one is edible. All of the halogens are also extremely reactive, just like the alkali metals. They're rarely found free in nature. And fluorine, that's the most reactive of all halogens. Last thing, the noble gases are this last column furthest to the right on the periodic table. As we know, these do not react a whole lot. They are all odorless, colorless, and non-flammable. The group includes helium, neon, argon, krypton, xenon, and radon, and they do not like to bond with other elements or other atoms of the same type. They really just sit on their own. So a lot of this information comes from just a variety of sources, but all of the dates and any kind of detail stuff did come from Botanica, just so you all kind of know what the source is on that. All right, good luck finishing up those notes. Let me know if you have any questions, but hopefully the goal today is that you know the names, right, of these groups. And again, this periodic table is nice because it has them keyed right there. You know a little bit about them. So remembering left side are the metals, right side are the nonmetals. This is the most reactive group of the metals. This is the most reactive group of the nonmetals. And just some of the characteristics we talked about with noble gases not bonding very often and being odorless and colorless, etc. And all of those things we talked about. So thanks for your time.